Hello everyone, in this lesson we'll be talking about factoring polynomials. Specifically, we're going to be factoring two special cases of polynomials. The first one is the difference of squares. So what is a difference of squares? Specifically, it is a polynomial of the form a squared minus b squared. Some characteristics: it's always a binomial. Each term is a perfect square, and the second term must be negative. If that was a bit much to digest in one point, let's go ahead and look at some examples. So a simple example would be something like x squared minus 9. All right, let's check off some of the characteristics. It's a binomial, two terms. Each term is a perfect square. X squared and 9. We can take the square root of those and they come out evenly. And the second term is negative. We circle the sign in front, that's negative. So that's a difference of squares. 64x squared minus 144 is a difference of squares. 361x squared minus 256. We need to know those perfect squares up to 400 again. And then another one that would be a little bit sneakier is when we see something like 169x to the fourth minus 225x squared. Hopefully you recognize right away that the coefficients are perfect squares, but if we take the square root of x to the fourth, we get x squared, and we take the square root of x to the second, we get just x. Remember, the square root is like a half power, and if we multiply power, we have power of powers, we multiply the exponents. So 4 times an exponent of a half would be 2, and 2 times an exponent of a half would be 1. Some non-examples would be something like 4x squared minus 8x plus 16. Yeah, we've got a perfect square here and here, but we've got a trinomial. Another one would be something like 20x squared minus 100. It's close. We've got a perfect square here, x squared is, but that 20 is the problem there. So that does not work out. So let's go through and look at a few examples and see if they are difference of squares. Is 16x squared minus 9? Yes, that is a difference of squares. What about 20x squared minus 49? No, because this is not a perfect square. What about 121x squared plus 81? No, trying to be tricky. There's addition in the middle there. So even though both terms were perfect squares, it is not a difference of squares. Okay, but now we need to actually know how to factor it. In previous week, we were pulling out a greatest common factor, but there's a new, different way to factor these kinds of expressions. So step 1 is going to be to take the square root of each term. And then step 2 is going to be to put the square root of the first term plus the square root of the second term times the square root of the first term minus the square root of the second term. Sorry, I didn't really provide nearly enough room to write all that in there. And it is a mouthful, but once we see it in practice, I think you'll realize it's not as hard as it sounds. Okay, so let's look at 225x squared minus 289. First, we recognize that 225x squared, that's a perfect square. 289, that's a perfect square. And we have subtraction in the middle. So the steps say to take the square root of each term. Square root of the first term is 15x. Square root of the second term is 17. So we're going to take 15x minus 17 as one term, and 15x plus 17 is another term. And that's it. That's our answer. So it was the square root of 1 minus the square root of the other times the square root of 1 plus the square root of the other. So this is the factored form. Now, that's your answer. Let's just talk about what this means. It means that if we were to multiply these two, which would require foiling, we would get back to where we started. So don't do this when you're solving problems unless you're looking to check, because this is your answer. I so often see students go ahead and take all the time to do the foiling, and then they circle the original answer as their answer. So if I go ahead and take 15x times 15x, I get 225x squared. And then I can take 15x times 17, and I'll get 225 plus 30 is 255. And then I'll do it on the inside, so I'll get minus 255x. And then last terms I'll get is negative 289. So these terms here in the middle, because one's positive and one's negative, cancel out. And then I'm left with 225x squared 225x squared minus 289, which is what I started with. That is like a check step to make sure that this was your correct answer. So remember, the factored form is the answer we're trying to reach. Okay, let's go ahead and do another example. This one often throws people off because they look at 1 and like, well, that's not a perfect square. Well, actually it is. Let's go ahead and start. We'll take the square root of the first, that's 14x, minus the square root of 1 is 1. So that's our 1 term. This time we put the minus in there, and then the plus next. And does it matter if I put the plus first or the minus first? No, not at all. That is our final answer. Let's go ahead and just look at another example that's a little bit more advanced. Here we see not just x squared, but an x to the fourth and then an x squared. So the square root of 169 is 13. The square root of x to the fourth is x squared. Okay, this time I'll put the plus first. 361, that square root is 19. The square root of x squared is x. And that's our first group. And then our second group is going to be 13x squared minus 19x. And that is how we factor difference of squares. Let's now look at a second special case. In this special case, we're going to be talking about something called a perfect square trinomial. So a perfect square trinomial is a polynomial of the form a squared plus or minus 2ab plus b squared. So what are some of the characteristics? First, it's a trinomial. Second, the first and third terms are perfect squares. Lastly, and this is the most complicated one, the middle term is twice the product of the square root of the first and third terms, ignoring the sign. One last characteristic is that the last term is always positive.
Whoa, must be Burt Reynolds or something.
Okay, so let's look at some examples and dissect what all those characteristics really mean. So one example would be 4x squared plus 12x plus 9. All right, let's go through them. First, it's a trinomial. Definitely, we've got 1, 2, 3 terms. Great. The first and third terms are perfect squares. So this term is a perfect square. Yeah, the square root of that is 2x. This term is a perfect square. Yeah, square root of that is 3. Let's make a note of those. Square root here was 2x, and square root here was 3. Okay, so the middle term. The middle term has to be twice the product of the square root of the first and the square root of the third. Well, those are the numbers in purple here. 2x and 3 are the square roots. Well, we have to double that. And if we take this, 2x times 3 times 2, we get 12x, and that's the term right there. Great. And then the last qualification that has to be true is that this right there has to be a plus. So that is an example of a perfect square trinomial. Let's get some more examples. Another one would be x squared plus 2x plus 1. First is a perfect square, last is a perfect square. Square root of that is x times 1 is x times 2 is 2x. Last term is positive. Another one would be 25x squared minus 40x plus 16. Okay, first is a perfect square, last is a perfect square. That's 5x times 4 is 20x times 2 is 40x. And we do ignore the sign when looking for the middle term. Okay, what are some non-examples? 9x squared minus 3x plus 1. The first and third are perfect squares. We have a plus sign for the third term, but the square root of this is 3x. The square root of this is 1. And then we double it. So we would end up getting 6x. That's not our middle term there. Something like x squared plus 2x minus 1. It looks close to our other example that does work, but we can't have a minus there. That's a problem. Okay, so let's go ahead and look at some examples and determine whether they are perfect square trinomials or not. All right, what about this first one? Okay, best to do the work as we go. Square root 4x, square root 3. 4x times 2 times 3x, that's 8x times 3 is 24x. Great. And so this term is also positive here, so that meets all the qualifications. So yes, that's a perfect square trinomial. All right. Is this a perfect square trinomial? Well, right off the bat, that's not a perfect square, so no. All right, let's look at the third one here. Square root of this, that's 11x. Square root of 9, the third term, 81 is 9. Great. All right, if we took 11x times 2 times 9, well, 11x times 2 would be 22x, times 9 would be 198x. And that is not the middle term. So, no. So all of that is just to determine whether or not we have a perfect square trinomial. Once we know that we have a perfect square trinomial, it's time to factor it. So there's 3 steps to factoring a perfect square trinomial. The first step is to take the square root of the first and third term. And the good news is, as we were checking it already to see if it was a perfect square trinomial, we already really accomplished this step. The second step is to check the middle term is twice the product of the first and third. Again, that was still really part of establishing whether it was a perfect square trinomial. Now, for this third step, we're going to put each square root in parentheses and square it. And in between the two terms, we're going to take the sign of the original middle term. And that's going to go right there. All right, so much processing that has to be done. Let's go ahead and actually look at what really is involved, and I promise it's less scary than it seems. Okay, so we begin. We take the square root of the first, 2x. Square root of the third, 3. We check 2x times 2 times 3. That's 4x times 3, 12x. Good, that means it works. So we're going to take that first square root, 2x. We're going to take that third square root, 3, put them in parentheses with a square there, and then this is really the next step, that last part down here of step 3, is we're going to take the sign that was in front of the original middle term. So this is 2x minus 3 squared. And you might be thinking, that looks so bizarre. Well, what does this really mean? It really means that we have 2x minus 3 times 2x minus 3. So we're used to kind of seeing two groups like this multiplied together, and so there they are. They're just the same exact group both times. We could go ahead and FOIL this, and we would realize that we would get the exact term, the exact expression that we started out with at the beginning. But this is our final answer. It's a perfect square trinomial. It turns out to be two binomials that are exactly the same multiplied by each other, so that's why we just square the binomial. Let's do a couple more together. All right, so take the square root of the first, 14x. Take the square root of the third, 1. Is 14x times 2 times 1 equal to the middle term? Well, that's going to give us 28x. Yes, that's correct. So we open our parentheses, square root of the first, square root of the third. It gets squared. We take the sign that's right there in front of the middle term originally, and that is how it factors. 14x plus 1 squared. All right, let's look at another example. Let's look at x squared minus 18x plus 81. Square root of this is x. Square root of that is 9. X times 2 times 9, that's 2x times 9, that's 18x. Yep, 18x. So we take the square root of the first, x. We take the square root of the third, 9. Put them in parentheses, squared. The sign of the middle comes down, so that's x minus 9 squared. Well, what happens when we have examples that are a little bit more involved? Let's go ahead and jump into this brutal looking number 9. All right, so x to the 20th. Is that a perfect square? Well, imagine taking the square root of it. Square root is the same as a half power. So if you're going to take it to the half power, we multiply those exponents. So 20 times a half, yeah, that comes out nicely to just 10. And then y to the 12th to the half would be y to the 6th. Okay, so is x to the 10th times 2 times y to the 6th, what does that give us? Well, 2x to the 10th, y to the 6th, and that is our middle term. Okay, so we have x to the 10th is the square root of the first. We have y to the 6th is the square root of the third. Put them in parentheses, square it, bring down our sign. Wow, it looked mean and evil. It really wasn't that bad at all. So these are two special cases. This is how you factor the difference of squares and how you factor a perfect square trinomial.